the different energy levels of electrons. And what's important to note is that I would write this down if I were you. Out here on the right, where the binding energy is low, these are electrons far from the nucleus. Since the binding energy is going up, the farthest left peaks, those are the electrons that are closest to the nucleus. Those are the ones that take the most energy to remove. So over here we have electrons that are close to nucleus.
Right there.
Okay, now since we're dealing with the electrons that are close to the nucleus, let's see if we can make sense of this PES data. This peak is a certain height. Those are the electrons that are closest to the nucleus. This peak is the same height as the first peak. Now, what do you know about atomic structure and electron arrangement that would indicate that that peak should be the same size as that peak? What do you know, Nathan? Oh, you're doing the stretch. They are. What electrons are closest to the nucleus? The 1s. How many electrons are on 1s?
2.
Right. What's next? 2s. 2s has room for 2 electrons. That's why this 1s peak is the same height as that 2s peak, because they can both hold 2 electrons. Look at the y-axis, the relative number of electrons. That peak's the same as that peak because it's the same number of electrons. What's next after 2s? 2p, which has room for more electrons, and so the peak can go higher. Now, if I have you come over here and look at this spectrum, remember that as we start to the right and go left, the energy is increasing. These are the closest electrons to the nucleus, and then these, so they're going farther up. So that means that this must be 1s, this must be 2s, and this must be 2p. The question they're giving, which element could be represented by this PES data or spectrum below? Now, they don't give any numbers of electrons on here, but you do notice the first spike is the same size as the second spike. That should make sense. And more specifically, it looks like 2, 4. This first spike is 4 lines high. This spike is 4 lines high. Sounds like, I mean, this is 1s and this is 2s. Sounds like every electron is going to take up 2 lines. Well, this spike, 1, 2, 3 electrons. What element is this most likely the PES for? That would be nitrogen, that's right. 2 electrons in 1s, 2 electrons in 2s. 2p is bigger, it looks like it's a third bigger. So that would be, I should say 3 over 2 bigger. That would be nitrogen. That's how you use PES data. Andrew, you ready? Let's see, we can slide your desk out to the hall.
You got this, Andrew. Way to go.
You're cheering for him. That's good. That's good.
Sure, they said don't get it.
Sure, they said what?
Just do it. Shut up. You're so mean, Janet. Let me see it.
No!
I want to see it.
You can see it from here.
Okay.
You can see it.
So I'm going to jump. There are a couple other sample questions like this, but I want to show you. Hi. Who's that?
Yes! Bye! Bye! No, you need to do the special edition promo.
Okay. I want you to take a look. This question is kind of spread out. It was over 2 pages. Here's the question, and then here's the data that it gives you. They say, okay, here's the original Bohr model of carbon. Now, carbon we know has 6 electrons. The Bohr model had room for 2 electrons on the first ring and room for 8 electrons in the second ring. Carbon only needs 4 electrons on the second ring, and then it's got all of its electrons accounted for. Is this picture using the Bohr model consistent with the photoelectron spectroscopy data given here. Is this consistent with that data?
No.
There's three.
No, it's not.
There's three.
Andrew, why not?
Wow.
Three orbitals.
Other Andrew.
There's no lifeline here, Andrew. What's the answer, Paul?
They'd be like the same distance.
Shouldn't one be the same distance? Well, what do you mean? You got 2 electrons that are closer to the nucleus than 4 that are out farther. What do you mean the electrons should be the same distance?
Like, because
Nathan?
the two
Yes. Yeah. If we have 2 in one energy level and 4 in another, shouldn't the one peak be twice as big as the one before it? Because, yeah, I mean, the peaks, remember, are the relative number of electrons. Which one do you think is more accurate for describing carbon? Electrons having 3 peaks, or this picture? Which one is more accurate based on what we've learned about atomic structure? Is the PES graph more accurate, or is the Bohr model more accurate? PES. And what is this telling us? What does the first peak represent? That's the 1s electrons. And how many do we know are in 1s? There's 2. Well, that's consistent with this one. But then where this one seems to fall apart is the second energy level doesn't have room for 8 electrons all the same energy, because some of them are that energy, some of them are that energy. What's the difference between those 2 peaks? One's 2s and one's 2p, isn't it? And now we know that for carbon, its electron configuration is 1s2, 2s2, 2p2. So it's got 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. And that 2s and 2p is not reflected by this picture, is it? This is not indicating anything about a 2s and a 2p. This just shows a second energy level that can hold 8 electrons, all the same energy. Well, now we know from the Schrodinger equation that those 8 electrons are not the same energy. 2 of them go in 2s and 6 of them go in 2p, if you have all that, yeah.
So how would it look? How would the correct one look?
The corrected Bohr model would need that second energy level broken up into 2 different sublevels. That's where we get the spherical shape for 2s and then the dumbbell shape for the 2p. They're not all the same energy. The 2s have a different energy than 2p. That's why we have that broken up into 2 spikes. Okay? So that's what it's getting at. What are you saying, Vince?
How does the fluorine make that 6 electrons
This is carbon.
Oh, it's carbon.
Yeah.
Wait, oh, wait, is that
Oh yeah, yeah. Number 4 is about it's got stuff down below. Yeah. The question is actually way up here, and then the data's right here. Yeah, because it was a page break. So.
I was like, what?
Let's see. I want to take a look at this fluorine question, see if we can answer that one.
No.
Yay.
Okay, so this is the blue P. I don't know if you can tell. You can probably see the pink. The pink spikes are for fluorine, and then the blue ones, this, and this are for boron. All the fluorines seem to be to the left of the borons. Why would that be? Remember how it goes. The binding energy, which is the energy holding the electrons there, increases as we go to the left. So what it's saying is it's more difficult to remove the electrons from fluorine than it is for boron. Why? Why is that? Because it's smaller. That's right. That's exactly why. And the effective nuclear charge, fluorine has a bigger nucleus. They're in the same row, so it's the same energy level. Fluorine with the bigger nucleus is holding those electrons more tightly, making it small. Yep. B, why is the one peak in fluorine, which is that one, so much taller than all the others?
There's more of them.
Yeah, because this represents 2p5. It's 5 electrons. It's just a taller spike because there's more electrons in that energy center. That is the 2p for fluorine. This is the 2p for boron, which only has 1 electron in it. So it's 1/5 the size of that. That's the only difference in the size of the peaks. Okay, now I'm going to take you back to this. I'm just going to show you one more, and then we're going to be done. Okay. Now, this is going to ask a question, and then give the answer. Let me see if I can make this a little bit bigger. Whoa. Yeah, well, I guess I'm not going to make it bigger. So the question is up here. They give you 2 different PES data sets. Which of the following best explains the relative positioning and intensity of the 2s peaks only in the following spectrum? So this is the 2s electron in lithium. This is the 2s electron in beryllium. It shows that the beryllium 2s electrons are farther left, which means it takes more energy to remove beryllium's 2s electron than lithium's. Why? What do you know about beryllium and lithium to indicate why the graphs of the PES data would be like that? Here are choices A, B, C, and D. They're tiny. That's why I was trying to make it bigger. Do you have an answer choice, Andrew? Okay, look at your options. Which of these 4 is the reason for that difference? We're only looking at 2s. Okay, go ahead, give me a shot.
I'm going to go with C.
You're going with C? Anybody else like C? C's not right.
Oh, really?
Can it be A?
A is right.
A.
Yeah. It says lithium has a greater pull from the nucleus on the 2s electrons. If that were true, lithium's spike would be farther left.
So Kathy.
I have something for Jacob Smith.
Okay.
Oh, that guy.
Thank
you very
you.
much.
Here you are, sir. Okay, now, A was the right answer. Beryllium has the greater nuclear charge. Now, we both have beryllium and lithium pulling on the 2s electrons. Because beryllium's nucleus has more protons in it, it's more positive, that's drawing the electrons in, making it more difficult to remove them. So it takes more energy to remove the electrons in beryllium. And notice the size of the spike. Lithium spike is half the size of beryllium spike because lithium only has 1 electron in 2s. Did I say that right? Lithium only has 1 electron in 2s. Beryllium has 2 electrons in 2s. So it's got a spike that's twice as big. That's it.
Are we quitting?
That's it for today.
See ya,
Bye,
Angela.
Angela.